What are the expected readings of the following in the figure below? R is equal to 6.7 ohms, delta V is equal to 6.9 volts. Part A, an ideal ammeter. Part B, an ideal voltmeter. Alright, so this is the circuit that the problem gives us, and here I labeled points A, B, C, D, E, F, G, and H. Notice that I put in the values of 6.1 volts for this battery, 4.5 volts for this battery, 6.7 ohms for this resistor, 5 ohms for this resistor, 10 ohms for this resistor, 6.7 ohms for this resistor. And this A symbol here is an ammeter, and this V symbol here is a voltmeter. And when I first looked at this problem, I realized that the current from here in this wire is probably going this way, because this is where the high potential is, and we know the current always points away from the higher potential. Similar thinking down here, we got the current number 2 pointing away from the positive terminal of the battery. And down here, the directions that you choose are really arbitrary, but for me, I chose the current in this wire all the way around here to be going this direction, and I chose the current in this top wire up here, again, to be flowing in this direction. And my thinking behind this was that this current's already pointing that way, so this current's probably going to want to go this way to get back to the negative terminal of the battery, again up here. So you're looking at this, and obviously you can see the 3 different loops. We got one loop right here, one loop down here, and this big loop right here. Also, there's a loop right here. That one's kind of complicated. We don't have to mess with that. Starting off with our first loop, I'm going to go from here all the way around back to here. So I'll label it D, C, A, B, D. And going this way, since there's an increase in potential, I'm going to keep that as positive 6.9 volts. And then since we're going with the current here, there's going to be an energy loss, so it's going to be minus I1 times 10 ohms. Again, following the circuit of ground. Assuming an ideal ammeter, there will be no resistance, so we could just forget about that one. And then over here, we still have current number 4, and since we're again going in the direction of the current, we're going to be having a loss of energy. So minus I4 times 6.7 ohms. And then we're back to where we started. And due to Kirchhoff's rule that going in a loop, all the charge must be 0, the net charge must be 0, this allows us to write this equation for the first loop. Alright, that's one equation down. You just need 2 more to go. Or maybe 3. So this loop down here, F, E, G, H, F. Again, an increase in the potential since we're going from the negative terminal to the positive terminal. Going with the current, so this is going to be minus. Again, down here, going with the current, so this is also going to be minus. And then back to where we started. And again, due to Kirchhoff's loop rule, it's just equal to 0. Now that's good. We got 2 equations, but we have 4 different variables. Current number 1, current number 2, current number 3, and current number 4. That means we need 2 more equations. Let's get working. So now let's take a look at this outer loop here, AGHBA. Going along here, there's no resistors, no energy loss. Right here we have a resistor. We're going with the current, so we'll keep that minus. Alright, going back around, no more resistors, no more resistors. Hit another resistor. This time we're going against the current, so it's actually going to be an increase in energy. Again, Kirchhoff's loop rule, equal to 0. And now I'm looking at this one, and I'm seeing something pretty peculiar here. It's the same amount of resistance in the resistors, but yet there's a different amount of current. If I add the third current times 6.7 ohms to the other side, I get out of the fourth current times 6.7 ohms is equal to I3 times 6.7 ohms. Since they're the same thing multiplied, current number 4 is equal to current number 3. I'm feeling that will be useful later. But we still have 2 equations, 3 variables, so we need another equation. And I could do another loop rule right in the middle, but I'm just going to keep it easy and go with the junction rule. Looking at points E and C, together there is charge number 1 going in and charge number 2 going in. And out of it we got charge number 4 and charge number 3. Now I could go through the intermediate step of having a 5th current right here, and then having I1 equal to I4 plus I5, and I5 plus I2 equal to I3, and then just solving. But I could just treat C and E as kind of coexisting at the same point, which will allow me to write I1 plus I2 is equal to I4 plus I3. Now don't go crucifying me over this, it's completely legal. Because if you look at it, due to the conservation of charge, the total charge going in here must also equal the total charge going out. So what if the sum's going up and sum's going down? The total in has to equal the total out. And then we know that this is equal to that. So actually we can write this. Very nice. Now you're looking at this, you got this equation right here, this equation right here, and this equation right here. We got 3 equations, 3 variables, as long as you replace I4 here with I3. Now that's very nice. I'm not going to show all the tedious steps of solving a system of equations, but at this point in your career as a Marist High School senior taking AP Physics and either AP or Honors Calculus, this should not be a problem to you. So I'm going to assume that you know how to solve this. Solving all these values result in I1 of 424 milliamps, I2 of 367 milliamps, and then plugging these two into this equation, adding them up and dividing by 2, yields I3, which is 397 milliamps. And this, my friend, is equivalent to I4, which is the current that runs through the ammeter. So that is your answer to part A. A lot of work for one part of a problem. And for part B, it asks us to find the voltage reading across this voltmeter here. So when I was doing this, intuitively, I know the answer is just 2.4 because this is at 4.5 and 6.9. But I was wondering if there was a more quantitative and rigorous method to prove it. And I realized that I could kind of treat this in here as its own little personal loop. So we'll go from here, over here, up here, back here, and then down there. And with this little loop here, we're going this way, an increase in potential. So we're allowed to write 4.5 volts. And then we're not sure what the current is. So we'll just put V question mark for what we're trying to solve. Very academic. And up here, we're going decrease in potential from the positive to the negative terminal. So it's going to be minus 6.9 volts. But since we're going to the loop, we know this has to equal 0. And now, doing some simple algebra, V question mark is equal to 6.9 volts minus 4.5 volts. So then our question mark V is simply equal to 2.4 volts. So intuitively, you can see that they're at a potential difference of 2.4 volts. But using Kirchhoff's loop rule allowed us to prove that our intuition was correct. When I was first doing this problem, I was having difficulty deciding what should be positive and negative in our equations using the loop rule, because I wasn't 100% certain on what happens with the current in the resistors. But now I know that when you're going with the current across the resistor, it results in a decrease in energy, resulting in a negative sign. When you're going against the current, such as up here, you get the energy is actually increasing. So you'd have a positive current times resistance. The same with the batteries. Going from negative to positive, you're increasing energy, so it's going to be an increase in energy. Going from positive to negative, you're decreasing the energy, so their corresponding voltage difference is negative. And overall, this problem shows my growth because it shows that I could analyze more complex circuits rather than just those with one battery. And I'm able to effectively solve for the current and eventually the voltage across each different resistor. Thanks.